right, welcome to Unit 10. We're going to start this unit by looking at our learning targets. So we're working with some exponential functions here, what it means for a function to be exponential, to understand image and features of the graph, and to be able to evaluate and use exponential functions. So before we get started, I want you to answer two questions for me. And the first one is, what do you already know or remember about exponential functions? And the other one is, would you rather have the ability to fly or have the ability to turn invisible? So go ahead and pause your video, answer those two questions. All right, we'll get back to that superpower question in just a minute. My next question for you is, would you rather have $100 a day for 1 month or 1 cent the first day, then doubled every day for 1 month? So go ahead and think about that. Circle which one you think you would rather have. And now let's start doing some calculations. So when we talk about a month, we're going to talk about a 30-day time period. You don't have to write this down. Just go ahead and listen, pay attention a little bit. So that means that on the first day, if I chose option 1, it means I get $100. Second day, I get $100. Third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. We're going to stop after the 11th day. I would have $1,100. So then if I think about option 2, which is 1 cent the first day, that means the next day I get 2 cents, which means really I have a total of 3 cents. Then the next day I would get 4 cents, which brings my new total to 7 cents. And then I'm going to get 8 cents. So now I have 15 cents. Going to need a dime to help me out there. Then I go to 16 more cents, and then I'm going to be at 32 cents, and then 64. And then this day I get $1.28. That's pretty exciting. Then I get $2.56. Those of you that have played 2048, these numbers should be looking familiar to you. Then I get $5.12, and then I get $10.24, which means at the end of the 11th day, I have $20.47. So go ahead and think about your answer. Think if you want to keep the same one you chose or if you'd like to change at this point after the 11th day. And then I'm going to flash forward through the magic of video making, and I am going to jump to after the 20th day. So the 20th day, I'm going to have $2,000. Hopefully that makes sense to you. On the 20th day here, so this would have been 1024, and then I would have gotten 2048, and then I would have had 4096, and then I would have added to that 8192, and then $163.84 on the 15th day would have been added to my account. And by the time I get down to the 20th day, I end up with $10,485.75. Now, if you don't believe me, you can calculate through days 14, all the way out till day 20. But already by day 20, it looks like it is a much bigger advantage to have started with a penny, doubled every day, and added to my total. In fact, if we use the power of video magic, at the end of 30 days, I would have $3,000, or I could have that is $10,737,418.23. I think most people would agree this would be the way to go. So why does it happen in that way that your numbers grow so large so quickly? And that has to do with an exponential function. When something is growing exponentially, it means that our variable is in the power. So that's why I asked you a superpower question. Get it? Superpowers, powers, etc. Anyway, so an exponential function has a base of b, and it's being raised to a variable. So in this case, x is our variable. B is greater than 0, and b is not equal to 1. So let's talk about some restrictions. First of all, if b were equal to 1, then we just get 1 raised to the x power, and 1 to the first, 1 to the second, 1 to the third, 1 to the fourth, 1 to the fifth. That's just the line y equals 1, and that's boring. right? That's not going to be an exponential function. It's not going to have exponential growth for us. We're just going to be at the horizontal line. The other thing to consider then is if b were negative, we would have something like negative, let's say 2 to the x power, which means that when x was a odd power, we would get a negative number. But then when x was an even power, we would get a positive number, and then a negative number, and then a positive number, and a negative number. And your graph would be jumping on either side of your axis at all times. So we don't want to have this alternating pattern. So if b was less than 0, we would have an alternating pattern, and we don't want to be looking at that for our smooth curve. So the next thing I'm going to ask you to do is to recall your properties of exponents. So thinking about each one of these scenarios, see if you can fill in an answer to simplify each one of them. Go ahead and pause your video. All right, hopefully these came back to you, that if you are multiplying two functions that have the same base, you can add their exponents. If you are dividing two things that have the same base, base b, you can subtract their exponents. b raised to a negative power, that negative sign just means take the reciprocal of. So it's going to take our b to the x and then put it on the bottom or in the denominator. Anything raised to the 0 power is going to be a value of 1. Any number raised to the first power is itself. Here we have a product being raised to a power, so we can think about that as a to the x, b to the x. Here we have a power being raised to another power, so we're going to multiply. And here we have a fraction being raised to a power, so we can raise the numerator and raise the denominator. To help us with this example, I know this just popped up, but if I think about something to the power with that same base to another power, I could think about x to the third and x to the fifth. We know that that's going to be x to the eighth, because x times x times x, x to the third, x times x times x times x is x to the fifth, and then we get those total of x to the eighth. So if you need to stop and write them out, you are more than welcome to do so to remember those properties of exponents. All right, so graph by hand, f of x and g of x on the same graph, and then we're going to do some analysis of domain, range, and asymptotes. So I'm going to start with this f of x equals 2 to the x. So graphing by hand, I'm going to set up a nice xy chart. I'm going to pick -1, 0, 1, 2, and 3. So if I take 2 to the negative first power, that means 2 to the first, which is 2, but then remember that negative sign means take the reciprocal, so I'm actually going to have 1 over 2. 2 to the 0 is going to be 1, because anything to the 0 power is 1. 2 to the first is going to be 2, 2 to the second is 4, and 2 to the third is 8. So graphing that, I'm going to go -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. And I get kind of this curve happening. But unlike a quadratic, where it's going to curve back and create a parabola, as I continue to get further and further in the negative direction, I'm going to get tinier and tinier fractions. So we're going to approach 0. Next, then I'm going to graph our g of x is 3 to the x. I'm going to do the same values, -1, 0, 1, 2, and 3. So 3 to the negative first would be 3 to the first, which is 3. Then take the reciprocal, so 1/3. 3 to the 0 is going to be 1. 3 to the first is 3. 6. Nope. Hopefully you didn't just fall for that. That was me going too quickly. 3 to the second is definitely 9, and 3 to the third is 27. So I'm going to go through and plot these points. -1, 1/3 is a little bit lower than 1/2. 0, 1, that's going to be the same point. 1, 3, 2, 9, and 327 is already going to be way off the charts. Now you'll notice that this 0 threshold on the left, or numbers less than 0, our 2 to the x is a higher function than our 3 to the x. But once you move past 0, or numbers greater than 0, 3 to the x, the blue graph, becomes taller than the green graph, which is something we'll kind of look at throughout the unit. So thinking about our domain for an exponential graph is -infinity to infinity. You can raise that base to any power. Our range is only going to be from 0, not including it, till infinity. And our reason for that is, again, if you think about positive numbers, well, if you take a number raised to a positive, they're going to keep going up to infinity. If you take a number and you raise it to a negative value, it doesn't ever actually become negative. Instead, what ends up happening is you get a smaller and smaller fraction getting closer to 0, which brings me to the fact that there is a horizontal asymptote, y equals 0. We do not have any vertical asymptotes. We do not have any x-intercepts. Because if you look at this graph, it's never going to cross over the x-axis. We do, however, have a y-intercept, which by definition you're going to plug in 0 for x. You will get back 1 for y. And you'll notice that both of these, if we just talk about our general function, some number raised to the x, it doesn't matter what our base was, in this case 2, in this case 3, when you raise it to the 0 power, you always end up with that y-intercept of 1. All right, so graph by hand these two functions. I'm going to set you up with an XY chart, have you find the numbers and plot your picture, and then we'll compare. So let me get your XY chart set up. We'll go x 1/2 to the x. I'm going to go just with -1, 0, 1, and 2. And then we're going to also have in red x 2 to the negative x. -1, 0, 1, and 2. So see if you can fill out those two charts and graph your exponential functions. Pause your video. Surprise, they're the same graph. What? Well, if you think about this, we talked about the fact that this negative sign really means to do that power, 2 to the x, but then to take the reciprocal. So that would be 1 over 2 to the x. But then we could rewrite that as 1 over 2 to the x power, because 1 to the x is just 1. Now, if that didn't make sense to you, that's okay. We're going to keep working on it throughout the unit. But you should have ended up with these two same charts, and when you plot the points, you notice that they are the same. So if we think about asymptotes here, we are going to have a horizontal asymptote, still at y equals 0. X-intercepts, we're not going to have any x-intercepts because this is never going to be equal to 0. And our y-intercept, again, is going to be in goes 0 and out comes 1. Right? You can think about applying these exponents is to go step by step. So for instance, if I wanted to take 1/2 to the -1 power, that's going to be 1/2 to the first. Well, that's 1/2. Then that negative sign means take the reciprocals. So 2 over 1, which is going to give me an answer of 2. Something else you can notice, on our previous graph, we did 2 to the x. And this is 2 to the negative x. Well, that negative on the inside means a reflection over the y-axis. So instead of being our exponential graph that looked like this for our parent function of b to the x, if we do b to the negative x, it's going to reflect and look like that. So let's apply that concept of transformations. If this was our parent function, 2 to the x, and I applied 2 to the x plus 3 minus 7, well, this plus 3 is happening before I actually raise the exponent, or the exponential part, which is our function. So that means that I'm going to move to the left 3, right? Inside the function is a transformation left or right. Adding 3 would be a transformation to the left 3. Then, after I'm done with the function, 2 raised to the power, then what I end up doing is subtracting 7. So that's outside the function, which means I'm going to move down 7. It's a vertical change. So again, inside the function affects things horizontally, stretches, shrinks, reflections, moving. Outside the function is going to affect vertically. All right, the last thing then is to think about some questions for understanding. Go ahead and write down some answers to these questions. If you're confused on them, this would be a good starting point to talk about with your teacher when you see them next. But remember, an exponential function, parent graph looks like this. And you can transform it in the same way we've transformed other functions.